Hi, I'm Yuvashree from Vellore Institute of Technology, Chennai. Today, I'll be executing Project 1 of the NAND2TETRIS course. NAND2TETRIS course is a software in which we try to mimic the hardware using the codes. I've already downloaded the software from the official website NAND2TETRIS.org. Under the navigation bar, we'll find a section called Software. By downloading the NAND2TETRIS software suite, a zip file will be generated which we need to extract in our system. By extracting the files from the zip folder, we can see the two main folders. Inside the project, we have the stub file, test files, the compare and output files that we require for our project 1. Stub file, we implement logics in hardware description language, HDL. Given that we have the HDL file, we can verify whether it delivers the intended functionality of the underlying chip by loading this code into a given special program called Hardware Simulator, which we can use by clicking onto the tools Hardware Simulator, Windows Batch File. This is the interface for the software. Let me quickly explain the features of the software. Load chip, where we will load the HDL files. The HDL we load will be displayed here in static view. That is, we can't edit or manipulate unless using an external text editor. Load script. Load script is where we load the test script, test files, that is TST files. This will be shown over here. So let's get started with Project 1. Project 1, Boolean Logic. In this project, we are expected to build the following gates using the given NAND gate. NAND gate is said to be the universal gate since combination of them can be used to accomplish any of the basic operations. Here in the truth table, the output is high only when either of the inputs A or B is high or if neither is high. Using the NAND gate, let's implement the first gate, NOT. NOT uses one NAND gate, takes single input and produces the opposite of the input. If the input is high, the output is low, vice versa. Let's load the chip of the NOT gate HDL file, load chip, load the script of NOT file, TST. The yellow bar over here, which also means the cursor, will run through the program successfully and stop here. If it stops in middle of the program, that means some error is detected in our program. The input and output pins, we can change the input pins and accordingly the output pins will also change only when pressed with this evaluated icon. Now let's run the program with help of this option. As you can see, the yellow bar has successfully passed all the line. You can view the output now. Now in order to check whether our output is right, we can compare it. Since there is no change, the code we wrote is error-free and the logic is correct. Similarly, we'll execute the same for the other gates. Now, the second one is the AND gate. It takes two inputs A and B to execute. To execute AND gate, we'll have to use two NAND gates. Now I'm loading the chip. As the program runs, you can see that the input pins changes and output pins too. Let's see the output. Comparing, we see that the code is error-free and the logic is correct. Next, the OR gate uses 3 NAND gates. While I run, we can check the input pins and output pins changing. Let's see the output. Comparing, there is no change. We can proceed to the next. Over here, they have mentioned internal pins. Internal pins is nothing but, over here, we represent this part as the internal pin, C and D. So, we load the chip again for the next gate, XOR gate. XOR gate is not, we'll use 4 NAND gates. XOR chip. The script will be loaded here. Let's run and check the output. See the value changing. Output. Compare. So we'll proceed to the next gate. Multiplexer. In the multiplexer, we'll have 2 inputs and a selector, and let's see how the output show is coming. Load chip. Multiplexer. Script. Output, you can see A and B and the cell, which is nothing but the select. Proceed to the demux, is nothing but the reverse of mux. Here we'll also use the select and final gates. We can check the input and output pins and in the internal pin changing. Output, you can see the select here. Compare. No changes. The next gate will be AND 16, NOT 16 and OR 16, which is same as AND gate, NOT gate and OR gate, but here we'll use 16-bit. Let me show you. First we'll execute the NOT 16. We'll have 16-bit chip. NOT 16, load script. Carefully check the input and output pins. We will see some changes. You can see the values. Output. See, we'll have the 16-bit input and 16-bit as output. Compare. Similarly, we'll do for all the rest of it. And 16, and 16. Run. Compare. The same, so we can proceed to the R16. Load chip, load the script of R16 and run. See the values. Okay, now we'll proceed to the MUX16 code. MUX16 you can see 16-bit and a selector, two inputs of 16 bits and a selector. Now we'll run. If there is any error, it will show us. Okay, let's see the output. Compare. As you can see, there is no change. We can move on to R8-way. R8-way. Load chip. The script R8-way. Let's run and see. You can see there is A, B, C, D, E, F internal pins. Output 1, 2, 3, 4, 5, 6, 7, 8. So 8-way, 8 digits we can see. Compare. No change. MUX4-way 16. Let's run. No change. MUX8-way 16. Load chip MUX8-way 16. MUX4-way 16 we saw A, B, C, D, E and cell. Now here we'll see for MUX8-way 16 you'll see 8 that is A, B, C, D, E, F, G, H. Let's run and see if there is any error. See the values changing. Output. I can't scroll it sideways, so you can see the rest E, F, G when you scroll. So yeah, compare. No change. The next is DMUX, that is inverse. DMUX 4-way and DMUX 8-way. Let's check them now. So in the input pins, we only have cell and input. Over here, we'll have A, B, C, and D. Inverse of mux. So let's load the script, tmux, and run. No change. Now demux 8-way, the last gate. Here we'll have 8 output pin. Demux 8-way. Now let's run. You can see the 8 output A, B, C, D, F, G, H, compare, no change. So we have executed successfully the 15 gates that we have asked to implement or build using NAND gates. So thank you.